imaging in space with the Nancy Grace Roman Space Telescope Chronograph. And I will explain how it is possible to tackle the challenge of imaging exoplanets around very bright Earth stars combining hardware and software. And we're going to see also the challenges that the future high-contrast imaging instrument in space will raise. But first sorry, let's start with a little bit of context about exoplanets. So exoplanets, they are planets that orbit around other stars than our Sun. And as you can see on this very nice illustration, the exoplanets can be very diverse. And you can imagine that to detect and characterize those diverse population of exoplanets, you're going to need complementary techniques to do that. And among those techniques, you may have heard of the transit technique, one of the most famous techniques, which is pretty intuitive because we actually look at a planet that passes in front of the star, and we can see the brightness of the star decreasing in time and increasing again as the planet orbits periodically around the star. But what if we want to actually see the photons of the planets directly? So to do that, we need to use the direct imaging technique that consists in order to see the circumstellar environment, including the planets. And this is what the kind of thing that we can do with direct imaging. In this astonishing movie, what you can see is actually 4 gas giant exoplanets that are bigger than Jupiter, orbiting the HIT 799 star. So it was the first exoplanetary system with several exoplanets to be imaged, and it was imaged with Keck. And this movie spans 7 years of observation with Keck. So this is a plot of confirmed exoplanet as of today, and you can see that the transit technique that I was talking just before is a pretty successful technique. Discovered a lot of those exoplanets, and along with the radial velocity technique, the majority of planets have been detected by what we call indirect techniques. While the little dots, the blue dots that you can see here, are the exoplanets that have been detected by direct imaging so far. And we can see that there are just a handful of them, not so much. And it is explained very well because this technique is actually very, very challenging. Although it has a lot of advantages. The first advantage is, you can see it clearly on this plot, is that it actually targets a pretty different population of exoplanets than the indirect technique. The indirect techniques, they are kind of blind to those very widely separated exoplanets that are also pretty young and pretty massive and pretty luminous, especially in the infrared. So this plot actually show the mass of the exoplanet as a function of the semi-major axis. So those planets are, further from their star than those ones. So we can see that those techniques are actually complementary. So we can probe a different population of exoplanets with direct imaging. So that's the first advantage. And second advantage is that by detecting the photons of the planets at different wavelengths, it is actually possible to extract some spectrum of the atmosphere of those exoplanets and detect some chemical components such as water vapor, carbon dioxide, or methane that combine together may be the sign for life on another planet. So that's pretty exciting prospect. And the third advantage is that because we can see the photons on those images, we can also see the circumstellar environment of those stars, and we can probe the birth environment of those planets, and also by identifying interaction between the planet and the disk, learn more about how planets can form and characterize them a little bit better. So now that we talked about the advantages of direct imaging, we'll talk about the challenges, because there are a lot of challenges. We saw it's actually pretty difficult to see. To see those planets, we don't have a lot of detected planets with high contrast imaging. And so the first challenge of high contrast imaging is the contrast of flux between the star and the planet. It can be thousands to billions, tens of billions ratio between the flux of the planet and the star. And that's the reason why it's so difficult. And so in order to tackle this challenge, what we need to do, as I was saying before, is that we need an optical component that is called a chronograph that blocks the light from the star to see the circumstellar environment. So that's exactly really similar to the optical component that Bernard Liaw invented to hide the sun in order to be able to see the corona. And here in that image, you can see the moon acting as a natural chronograph during a solar eclipse in 2017, and that allows to see the stars around the sun. So the other challenges of high contrast imaging are to get a big enough telescope aperture to gather enough photon and be sensitive enough to detect very faint companions, and also to get the angular resolution that is necessary to separate the exoplanet from its host star. So that's another big challenge, because when you want to send a very big telescope in space, it costs of course a lot of money, as we could see with James Webb, for example. And another challenge is also the ability to extract the exoplanet spectrum to be able to characterize it. So we need to not only imagers but also spectrometers that allows us to do that. So now that we saw the advantages and the disadvantages, the challenges of this technique, we'll go a little bit deeper in the principle of chronography. And to do that, I really like to show those screenshots from a movie that is actually accessible on YouTube that was done by scientists and artists at JPL that explain very well the principle of a chronograph. So in this first slide, you can see a star what a star looks like through a regular telescope. Of course, the diffraction, the figure of diffraction here depends on the aperture of the telescope. And we need to block that starlight. So to do that, we use this optical component called a chronograph that has an opaque mask and that we put in the focal plane of our instrument, so that the starlight, the star that is on the optical axis of the instrument is blocked, but the planet that is off axis is actually not blocked, and we can see the planet and not the star. And in addition to this chronographic mask in the focal plane, which can be both amplitude or phase mask, we also have other components, sometimes in the entrance pupil, but very often in the pupil that comes after the focal plane mask. That blocks the light that was diffracted by the chronographic mask, so that we remove most of the stellar residuals. The problem is, when you do that, you still have a lot of stellar residuals in the final image. The chronograph itself can bring the contrast if it's really well optimized, such like in the Roman chronographic instrument. It can reach contrast of 10 to the -6, just alone, chronographic mask alone, but you still have a lot of stellar residuals. And to remove the stellar residuals, you can use combination of hardware and software. So the hardware is based on the principle of adaptive optics. And adaptive optics is a technique that has been developed mostly for ground-based telescope to tackle the issue of atmospheric turbulence that was limiting the resolution of big, giant ground-based telescopes. And the principle is pretty simple, and so you have a reference sensor that probe the turbulence, the atmospheric turbulence, and you have a deformable mirror that is used to correct in real time that turbulence. In space, of course, we don't have any turbulence, but we can use this principle of adaptive optics to correct in real time the slow varying aberrations of the telescope itself that are caused by some temperature variation, for example. And so by doing that, you're able to remove some, part of the residual starlight, but it's still not enough. You also need to add some post-processing algorithm to further push the contrast. And so those post-processing algorithms are combined with innovative, optimal observing strategies that consist in, for example, observing a reference star free of any circumstellar environment to calibrate the residual starlight and remove it from the image. And then you can see the planets and the fainter planets. So I really encourage you to check the full videos. There are 2 versions of it on YouTube, and it's really very nice. So now that we saw the principle of chronography and the main ingredients of chronography that are the optical component called the chronograph, the chronographic masks, the adaptive optic and reference sensing, and the post-processing, we will chat a little bit about the Nancy Grace Ronen Space Telescope chronograph. So what are the goals of this chronograph? So first of all, I'd like to tell people that this instrument and telescope and instrument is coming very soon. We just launched James Webb, but we are already looking forward this one, which should be launched in 2026 at the earliest. It's a NASA mission that's going to be launched to L2. And the goal of this instrument, which is a technology demonstrator, is to show that we're able to detect and characterize exoplanets at very, very high contrast imaging. The requirement is actually 10 to the minus 7, but the chronograph itself has been designed to reach much better contrast down to 10 to the minus 9. So as you can see on this plot, that shows the performance of various numbers of chronographs on different instruments, different telescopes. You can see here, for example, the contrast of flux that we are able to reach with Hubble, a couple of instruments with Hubble. You have the James Webb Space Telescope that just launched, and also what the ground-based instruments are able to do. This is the Ronen chronograph requirements here, but the chronograph design prediction is going to reach very close to 10 to the minus 9. And what's very exciting about this is that for the first time, we're going to be able to characterize directly some of the radial velocity planets that have been detected indirectly, and we will be able to combine the information that we have from both techniques to learn even more about those planets. So that very high-level contrast of 10 to the minus 9 is several orders better than the state-of-the-art chronographic instrument, as you saw. And it's all the more challenging that the Ronen chronograph has not been, the Ronen telescope has not been designed for chronography. And by that I mean that there is the entrance pupil is like a big, is occulted by the second mirror and has like thick spiders that really occult most of the primary mirror aperture. And so that makes the high contrast imaging very tricky, and it's a challenge it was a challenge to design chronographs that compensate for this aperture, very tricky aperture, to be able to reach those contrasts. So the Roman chronograph will it has been built from lessons learned from both ground-based and space-based instruments, space-based chronograph, and will also demonstrate for the first time some technologies that have never been demonstrating in space, such as, for example, the deformable mirrors that I was explaining just before, to remove the residual starlight, and also the use of EMC-CD detectors that is very useful for their photon content mode to be able to detect very faint signals. And of course, to detect those very faint signals, that also means that we're going to have to observe for a very long time, like for up to hundreds of hours. And during that time, the instrumental aberration will going to evolve they're varying very slowly, but they're going to be evolving. And so we will need this post-processing technique to be validated on that instrument to be able to reach the requirement. All right. So here is an overview of how the Roman chronograph will work. Here you have, first thing, the chronographs themselves with the pupil plane masks. You have 3 different modes that are shown here. You have more mode than that, but those are the fully, I would say, supported modes. You have an imaging mode, a spectroscopic mode, and another wide imaging mode. And you have the pupil plane mask, the focal plane mask, the Leo stop, as I was explaining before, and also field stop. So that's the chronograph. And as I was saying before, those chronographs are real gems because they are really being designed to handle the very tricky aperture of the Roman telescope. And also you have on this instrument 2 different systems of adaptive optics in one sense. First, the low order waveform sensing and control that use a separate detector from the science detector, and that will probe for the jitter of the telescope and also defocus, help for focus correction. The problem is that if you have a lot of jitter and the star is not well at the center of the chronograph will not be perfectly remove the stellar residual, so you really need that system to help correcting for that jitter. And then the second adaptive optic system is the high order waveform sensing control that is fed by the science camera directly, and that will correct higher order aberrations. All right, and I also talked a little bit about the post-processing technique, so I want to stop a little bit on this because that's also what brings me on Roman, because that's kind of my field. I've been, since the basically beginning of the mission, testing high contrast imaging, post-processing techniques on those high contrast imaging data. And each time we had a new design for the mission, we had to test those techniques of post-processing to make sure that we reached the requirement. So what's next? So the Roman chronograph is really the step forward, the future high contrast imaging instrument in space that will observe terrestrial planets in the habitable zone of their star. So those kind of instruments raise a lot of other challenges because we're going to have to go an order of magnitude higher or better than what we are able to do with Roman right now. And it's going to raise a lot of different challenges because of this very high contrast. And just wanted to mention that The National Academic latest Astronomy and Astrophysics Decadal Survey recommended this large space telescope that will include, that has first a big aperture of 6 meters, and it also will include a chronograph to block out the light from the bright stars. So we have 10 very busy years in front of us to demonstrate those kind of contrast for the future instruments. And one thing that I wanted to briefly chat about, looking forward to the future, is one of the work that is keeping me busy for a lot of years now, which is to implement model-based technique of post-processing on high contrast imaging. So I know those techniques are really, you're really familiar with those techniques here in that community, but in high contrast imaging, in the high contrast imaging community, it's really a hard sell because people don't really understand. The state-of-the-art techniques of post-processing right now for high contrast imaging mostly use principal component analysis using reference stars, observation of reference stars. So I found that those techniques are pretty empirical, they work well, but I think we can do much better and also envision co-design using. And I'm thinking ahead about how we're going to use those model-based techniques of post-processing to inform the design and how we can use also all the pre-information that we have about the model, about the observatory, to inform the post-processing. So that's really what I'm pushing really hard for. And we got awarded James Webb Space Telescope General Observer proposal to actually test those kind of techniques. And so we should get some first data on this in January. So I think the time is out. So if you want to learn more about it, I'm happy to talk more about that. Come to me or also ask me any question you might have. And I leave you with my conclusion slide, which summarize a little bit what I said, which is the direct imaging of exoplanets is one of the most promising technique to search for extraterrestrial life. And it's only possible by combining both hardware and software, and I know that you understand pretty well that concept here. And in order to further push the contrast and get unprecedented contrast. And finally, I really think the future instruments and future high contrast imaging instruments will highly benefit from applying those kind of techniques, model-based technique, to help and to inform also the hardware design. That's it.
Thank you very much, Marie. We're a little bit late, so maybe one question and the rest of the questions can go offline.
Really nice talk, thank you so much. My question is, why restrict yourself to just using an exoplanet foreground and a star background? More computational kind of approach would be required if your background was an extended source, such as a galaxy, for instance. So is there any value to doing that?
Yeah. You can use some techniques that enable to reconstruct some extended objects, and that's true that people are mostly, especially in high contrast imaging, more familiar with techniques to reconstruct point sources and having some forward model with point sources, but you can actually do also some pixel by pixel based reconstruction to reconstruct the full object and also reconstruct the extended sources as well.
I see. So exoplanets is just the aim of this particular mission that you're working on, but people do work on other things.
Yeah, the real goal is really to be able to detect a point-like source, of course. But yeah, you can also do some disk imaging, both exoplanet science and also disk science, and we really hope that we will be able to do that. However, the Ronen chronograph is a technology demonstrator, so we are not supposed to do any science with it. There may be the possibility to do science if the technology demonstration is successful and if we get some money to actually do science with it. So we will push very hard to be able to do that.
Thank you.
Thank you.
Okay, sorry, let's take the other questions offline, and let's thank our invited speaker again.
Afternoon, everyone. Am I audible? Okay. I think that was a great talk. I have been following James Webb Telescope pretty much religiously every day, so super exciting to know that there is one more satellite we can look forward to on a daily basis. The next talk will start off by looking towards the stars, but a little somewhere in between. We first have talk by Ronen, and do you want to set up? So the first talk will be on variable imaging, projection cloud scattering tomography, and the speaker will be Ronen from Technion. Right, get started.
Okay. Hi, everyone. I'm Roy from the Technion in Israel. I will present our paper, Variable Imaging Projection, Cloud Scattering Tomography. Clouds are extremely important. They regulate the Earth energy budget and are the source of fresh water. Clouds are a major source of uncertainty in climate predictions. By understanding 3D properties of clouds, scientists can hopefully understand the climate better. The atmosphere, including clouds, is a three-dimensional heterogeneous, highly scattering medium. Sunlight is scattered multiple times in the atmosphere, yielding cloud images. From these images, we derive scattering tomography, aiming to recover the 3D inner structure of small clouds. So, what does it require? First, we need high-resolution multi-view images from a wide angular range. Hence, we develop a dedicated space mission for 3D remote sensing of clouds, named Cloud CT, which is funded by the ERC. It will include 10 satellites flying in a formation. They will acquire simultaneously multi-view images of the clouds. To learn more, visit the Cloud CT website. If you would like to join this project and help the climate and your skills, contact us. We are hiring. There are two main bottlenecks to scale cloud tomography. The first is the downlink rate of data from space. For example, at 50-meter resolution, downlinking 2 square kilometers requires a second. On the other hand, tomography runtime is currently much worse. It takes about 1,000 times longer than downlinking data. In this work, we tackle the tomography runtime bottleneck. The observations are then mainly limited by downlink, making CT effectively real-time. Scattering CT is very different than medical imaging. In medical CT, the small-scale and controlled radiation enable a direct transmission model, which is linear. But in our case, the medium is huge, and the imaging is passive, relying on the uncontrollable sun. Image formation is the recursive 3D radiative transfer equation. This results in a nonlinear and very complex problem. Moreover, clouds are very diverse, as you can see. They are formed by chaotic airflows. This yields a real challenge for setting and learning priors for clouds. Also, images are taken from platforms at locations that vary between scenes. Moreover, some combine satellites of differing resolutions. Prior art on cloud scattering CT mainly relies on iterated gradient-based optimization. Due to the nonlinearity of the problem, physics-based methods are highly sensitive to initialization, while gradient computations are slow, making the approach unscalable. Moreover, they do not exploit rich knowledge of cloud structure, which can be learned. So, a learning-based solution named 3DeepCT was introduced last year. It is based on a simple convolutional neural network, hence operates really fast. But 3DeepCT has several limitations. It operates only on an array having fixed input and output sizes. Also, 3DeepCT uses inefficient learning, as each labeled datum is the complete 3D cloud. And it is designed only for a fixed imaging geometry. This makes 3DeepCT not applicable for real-world images. Our approach, termed VIPCT, handles these limitations. It solves It solves very fast and accurately the highly complex nonlinear problem of cloud scattering tomography at large scales. Moreover, our approach handles flexible imaging geometries and resolutions. Before we detail the VIPCT frameworks, let's compare our results to prior art. We immediately see that VIPCT runtime is about the downlink time limit, using only a single GPU in early 2022. By Moore's law, VIPCT is expected to be essentially real-time for space observations when Cloud CT will be in orbit. Moreover, VIPCT quality far exceeds prior art, as you can see, and it further improves with spatial resolution. Moreover, our learning-based result can initialize a physics-based solver, obtaining a lower error overall. Moreover, VIPCT is by design suited for variability in imaging geometry. We show this in extensive examples in our paper. Next, we describe VIPCT. Learning-based methods require a labeled dataset. However, measuring a large dataset of real clouds volumetrically in 3D is impractical. Therefore, we train using synthetic 3D clouds. They are simulated using coupled equations of a turbulent atmosphere. Then, we render images of ground truth things using a physics-based radiative transfer solver. This yields labeled 3D clouds and corresponding multi-view images. To make it more efficient, VIPCT focuses only on cloud voxels, which reside in a 3D cloud mask obtained by space carving. VIPCT relies on wide cloud images, while infers each cloud voxel independently. The output is the scalar of the extinction coefficient per that voxel. Inference for wide domains is fast because analysis of all cloud voxels is parallelized using a GPU. VIPCT encodes 3 information sources. The first is the cloud voxel 3D location. Clouds have some special trends. For example, they tend to be denser the higher the voxel is above the cloud base or in its core, away from the surrounding dry air, while atmospheric density tends to decrease with absolute altitude. These are trends that call for encoding of the voxel location. Moreover, a cloud voxel scatters more light at the cloud side facing the sun, so we need to encode the 3D location of the voxel. Next, the camera 3D location need to be encoded. This is because cloud appearance systematically varies with the view direction, particularly relative to the sun and the horizon. Moreover, encoding camera locations enables flexibility in the imaging geometry. Finally, VIPCT encodes spatial features in cloud images. Clouds formed by eddies at a huge range of scales, resulting in fractal images. To express this nature by features, we use multi-scale encoding, that is, an image pyramid. An image pyramid comprises operations that are efficiently implemented using a CNN. The parameters of the CNN are learned. This results in a feature pyramid network. More details are in our paper. Let us now run an example of a particular voxel. Using the known viewing geometry, we project the voxel location to each camera plane. The pyramid-based features are at the corresponding spatial location are then extracted. Each voxel thus yields a set of corresponding image features using projections in any variable viewing geometry. Overall, a voxel is represented by features of the voxels, cameras, and images. The features are concatenated into a single vector. Then a decoder estimates the cloud extinction scalar at the 3D location X. The decoder is a fully connected neural net, which is learned as well. So this is the overall architecture of VIPCT. But how can it work? This learning-based system has so many parameters to learn. The reason is the architecture, which makes training efficient. Recall that our architecture deals with each voxel independently. The number of labeled training data items scales with the number of voxels. This enables well-constrained training, even though the number of learned parameters is very large. Finally, we demonstrate our solution on a real-world data acquired by JPL's AIR-MISPI, which has 9 viewing angles. VIPCT is the first learning-based cloud tomography approach to operate on raw real data. The experiment has no ground truth. Hence, we assess recovery using cross-validation. We exclude a single image from the recovery process. Thus, tomography uses 8 out of 9 raw views. Then, we render the recovered cloud to generate the missing view. We compare VIPCT to a physics-based solver. The results, as you can see, are comparable. However, VIPCT runs at about 2 seconds. That's 5 orders of magnitude faster than prior art. Here we show another real-world cloud example. To conclude, VIPCT performs cloud tomography, which is essentially real-time, considering space-borne communications. It is a learning-based system relying on physically-based synthetic labeled cloud datasets. It works on real-world data, handling variable geometry by design. We hope that our research will provide a path for computational photography to utilize deep learning for analyzing volumetric objects. Thank you very much.
Thank you, Roy. Does anyone have questions from the audience? All right, we have.
Hello. Great talk.
Thank you.
I have a question which is like, I think pretty fundamental. I didn't really understand the loss of like, so you have this decoder that gives you put in a bunch of parameters about where your cameras are, where you see cloud, and where the location of the cloud. What exactly are you then penalizing on to get a cloud at the end?
So the output of the network is a single scalar of the extinction coefficient of the cloud at that specific point that you make your inference at. So the final loss is just the L2 norm between the ground truth synthetic scalar at that point and the predicted one through the decoder of the network.
Okay, cool. So I guess the follow-up on that is like in a lot of, sorry to bring neural radiance fields into this, but it has to show up eventually. In a lot of these sort of like test time optimization papers, you'll see similar sort of structure of you throwing a bunch of things into this large fully connected network, and you're trying to predict your termination, your extinction coefficient, whatever it is. Can you imagine like if I just gave you a bajillion gigabytes of that flight data without ground truth, without synthetic data, without this sort of like pre-training? Could you give me a test time version of this that gives you nice pictures of the clouds just from like kind of what you were doing for cross-validation of just like keeping out part of the data and trying to like re-render to different views and trying to sort of test that?
The problem here is to use your loss on the image domain, is that the forward rendering is a recursive, slow process. So you can't do it for this task of cloud tomography using current technology. If you will have a faster forward renderer, which is differentiable, so maybe you can do it without the synthetic data set, if I understood correctly your question.
Yeah, cool. Thank you.
Yeah, thank you. Great talk. I wanted to ask you, this is a problem of 3D reconstruction by multi-view cameras, but I was thinking that the shape of the cloud is dynamic, is changing with time. So is there any way to do synchronization between the multi-shots? I understand that it's like multi-shots from different satellites, and if there is no possible synchronization, then what was the latency between those shots, the difference, time difference?
Yeah. So
And one more thing, maybe you just mentioned, but I didn't remember. What was the voxel size for the output? Thank you.
yeah, okay. So I will begin with your first question. So because of that, that clouds are dynamics, so we intend to launch the Cloud CT space mission to acquire simultaneously the images. Using, for example, sequential imaging, like using this aircraft, this causes artifacts. And I have another work that was published at the ICCV last year. So, and there I show that you can do a 4D recovery of the cloud using a sequentially captured data. But of course, if you have more cameras simultaneously, it will work better. And what was your second question? So we use a 40 by 40 by 50 meters resolution. So about.
Yeah. Okay. So if you mentioned that you are using the multi views from plane, but also you show some slides with multi views from satellites. Do you use that or not?
So the satellites are from simulations.
Okay.
And this is experiment with real world data. The images are with 10-meter resolution, and the 3D voxel is about 40 by 40 by 40. So
okay, thank you.
You can use different resolutions. This is one of the advantages of this technique. You can use different resolution of the image and the volumetric voxel.
Yeah, thank you.
In the interest of time, let's continue. Thanks a lot, Roy. Let's give a hand. Roy has a poster, so definitely catch him and you can ask further questions. The next presentation is on the ground. We'll be talking about building hyperspectral cameras, and it's a do-it-yourself. So while we are set up, let me quickly introduce. The title is Do-It-Yourself Hyperspectral Imaging via Polarization-Induced Spectral Filters. This will be a virtual presentation, and the presenter will be Katherine Salesin from Dartmouth College.
What's going where? If you show me what you're trying to do, I can help you.
So this one.
That needs to go up there. Okay, we can do that. pause that. Change to control click. Option click, command click. Not when it's plugged in like that. Okay. 12 more panes of that are at. This is the worst thing I've ever done.
Hello, my name is Katherine Salesin, and I'll be presenting our paper, DIY Hyperspectral Imaging via Polarization-Induced Spectral Filters, co-authored by Dario Seyb, Sarah Friday, and Wojciech Jarosz from Dartmouth College. The inspiration for this project came from fun experiments like this, which show the kaleidoscope of colors you can create by placing strips of clear packing tape between two polarizers and rotating them. Normally, of course, this tape would appear transparent to our eyes, but we see these vivid colors because the tape is a birefringent material, which means that it alters the polarization state of the light in a way that depends on the light's wavelength. We were inspired to harness this effect to create a hyperspectral camera, but before we fill in the details of how this all fits together, let's briefly review hyperspectral imaging. Every color we perceive in the world consists of a spectrum in the visible wavelength range. An ordinary digital camera downsamples each spectrum to just 3 values, red, green, and blue. A hyperspectral camera, on the other hand, tries to capture a more complete representation of the original spectrum by sampling values across a larger collection of wavelengths. A typical hyperspectral camera accomplishes this by taking a series of images through a progression of filters that each have a narrow 5 to 10 nanometer window. These are typically expensive instruments costing thousands of dollars. Our approach is to use the less expensive ordinary digital camera, augmented with low-cost broadband spectral filters placed on its lens. The greater the variety of transmission spectra that these filters can achieve, the more useful spectral information can be gathered about the subject. We bring this concept to fruition by using the polarization-induced color that was our inspiration for this project. We use this polarizer wave plate sandwich to create spectral filters that have several desirable properties, including the capability to produce a huge variety of transmission spectra. Let's take a look at the transformations of light that produce these colors. If we were to look at a beam of light as a bundle of individual waves, each would have their own wavelength, amplitude, and polarization state, which could be vertical, circular, or elliptical. This light passes through a linear polarizer, which cuts the polarization orthogonal to its transmission axis, then passes through the birefringent material, or wave plate, which causes a wavelength-dependent phase shift that alters the polarization state of the light. It then passes through a second linear polarizer, which again cuts the polarization orthogonal to its axis. The cumulative effect is wavelength-dependent transmission. The transmission spectrum of a filter can be calculated analytically using Molar calculus, a mathematical framework for describing polarized light, given the rotation angle of each element, as well as the birefringence value and thickness of each type of waveplate. Since rotation angles are continuous, our spectral filters can produce a continuous gamut of spectra, whose range of expressiveness grows as waveplates are added to the filter. We describe an algorithm for choosing a discrete set of filters from this continuous gamut in the main paper. We show here some examples of how easy it is to produce a wide variety of filter transmission spectra by just rotating either the waveplates or linear polarizers in a 2-waveplate system. Clearly, these spectra are broadband in that they span the full visible spectrum, in contrast to a typical hyperspectral camera that uses many narrowband filters to isolate a tiny wavelength range. We clearly cannot use our filters to isolate a single wavelength in the same way. Instead, we pose this as an optimization problem. There are several prior methods that take a number of measurements of a scene by varying the lighting or sensors, and then use those measurements to solve for the measurement signal. We share the same underlying methodology as these prior works. However, these approaches all choose spectral variants from an existing discrete set, whereas our spectral filters can produce a continuous gamut of spectra, and therefore can take many more useful measurements. We also do not need to physically swap in or out any elements of the system between measurements. Taking more measurements is as easy as rotating the filter. Another class of approaches to hyperspectral imaging use dispersion or diffraction. Both of these methods bend light rays to spread spectral information over a spatial area, which in turn lowers the spatial resolution of the system. In our approach, we use temporal multiplexing to obtain spectral measurements, allowing us to retain the full spatial resolution of the image. The image model for our approach defines the pixel value recorded by the digital camera as the product of several terms: the camera's spectral response, the light source's emission spectrum, and the surface's reflectance spectrum, which is the unknown that we wish to acquire, integrated over all wavelengths. When we place our filter over the camera lens, the filter's transmission spectrum becomes part of this product. In order to solve for R, the reflectance spectrum, we convert these continuous functions to discrete vectors by sampling a set of n wavelengths, which also determines the spectral resolution of the system. If we then take measurements through our filters in various configurations, we can arrange all these measurements into one matrix and separate the unknown R from the rest of the knowns. This is now in the basic form of a linear system, which we can solve using a least squares solver with various constraints. The key idea here is that the more measurements are taken with distinct filters, the more over-constrained the system will be, which makes our filter design, which can produce an arbitrary number of distinct transmission spectra, especially powerful. Now that we've covered the theory behind our system, let's take a look at our prototype. To build our spectral filters, we use linear polarizers designed for casual photography that screw into a camera lens, and for our wave plates, we use clear packing tapes taped onto a clear lens filter. We label the angles around the edges of the filters, since estimating rotation angles precisely is important to the accuracy of our method. Aside from the digital camera, the total cost of these components comes in around $100. These are the simulated transmission spectra of 10 filters chosen by our filter choice algorithm from a 2-waveplate system and their sRGB projections. These real-world measurements of a color checker through these 10 filters shows that the tint of the color checker does appear to match the predicted color of the filters very closely. We reconstruct the reflectance spectra of the color checker squares using these 10 measurements and achieve reconstructions that mirror ground truth quite closely and are also comparable to recent prior work. We also tested our system on more complex scenes like this one, again taking a set of 10 measurements through the same 10 filters. And our system is able to successfully capture a hyperspectral image of this scene. We show further validation comparing real-world and virtual relighting of this scene in our main paper. Lastly, we show a variation of our system that trades off temporal multiplexing of our filters for spatial multiplexing, allowing our approach to become a single-shot strategy at the cost of spatial resolution. For this experiment, we cut out small squares of packing tape at varying angles and create a grid of them on the clear filter, allowing every grid square to become a separate filter. We then take measurements of a monstera leaf, allowing the leaf to occupy the camera's field of view. When we rotate the analyzer, we see the mosaic of morphing colors that are produced by the waveplate grid. If we use a single one of these photos consisting of 9 measurements for reconstruction, we get consistent but smoother results than if we use all 9 measurements from all these photos together for reconstruction, suggesting that as more measurements are added to the system, the relative importance of the smoothness term in the solver decreases. In all cases, the RGB color of the reconstructed spectra match each other and the leaf, and show a clear reflectance peak where one would expect for a leaf full of chlorophyll. To recap, we created broadband spectral filters with a continuous spectral gamut using polarization and birefringence. And we can take measurements of an unknown spectrum or scene using these filters. We can then solve for the unknown spectra by solving a linear system given the known camera responses and filter transmissions. And in in theory, we could use this procedure with materials of any price or quality level. But we construct a low-cost prototype of this design using an ordinary digital camera, linearly polarized filters designed for casual photography, and clear packing tape as the birefringent material. In the future, one could develop a more optimal algorithm for choosing a set of filters from this continuous space. We could also remove some assumptions of our light model using advanced physically based rendering. For example, we assume that incident light is unpolarized, and also that it enters normal to the filter plane. Lastly, we could build a prototype of our system with higher quality materials or even liquid crystals. One could imagine shrinking our filter mosaic down and placing it directly onto the sensor, like a Bayer mosaic. If liquid crystals were used, their birefringence could be dynamically controlled, and many measurements could be taken at an extremely high rate, which concurrent work has begun to investigate. For more information and a detailed tutorial on how to build your own hyperspectral camera, visit dartgo.org/hyperspectral.
Thank you, Katherine. I'm hoping that she can hear us.
I think you're muted on the Zoom, but
So I'm unmuted. Katherine, are you able to hear us?
Yeah.
Okay, awesome. It seems like I'll need this clip once again. Any question from the audience? We have time for a couple of questions. I have two questions, if there is any interest. I see that we have. Okay. The first question I have is, this version of tunable filters called Lyot filters uses a very similar architecture where you have thickness that increases exponentially, and then you have a rotating polarizer in between, and essentially it achieves narrowband spectral filters. Could you comment on how your work is similar or different from Lyot filters?
Yeah, definitely. Oh, sorry, I'm getting some feedback here. But it is the same basic physical mechanism. So it is the Lyot filter that are using the same basic principle of the polarizer, wave plate stack polarizer to create the spectral filter. And as you said, the goal with the Lyot filters is to create a narrowband filter. And typically they accomplish that by like adding more and more wave plates, or like thicker and thicker wave plates to achieve a narrower and narrower transmission spectrum. So ours is using the same underlying science and light phenomena, but with very cheap materials and also with broadband transmission spectra. So we're not trying to create a narrow wavelength range.
Got it. Thank you for that. Aswin, yeah. Can you hear me?
Yeah, so I was curious if, so when you're doing multiplexing the way you're doing to get the hyperspectral image, by using broadband filters and then demultiplexing out by solving a linear system, how much does photon noise play a role? Because in general, in these multiplexing systems, photon noise typically is the bottleneck to achieving high performance. I'm curious if something that you explored in simulations or something you observed when you're collecting real data.
Sorry, the question broke up a lot.
I'll repeat it for you. So Ashwin's question was, one of the problem with hyperspectral imaging is that you're often photon noise limited because of how much you subdivide the wavelength bands. What is the role of photon noise in reconstructions using your approach?
It's basically none. I mean, you are getting the noise that a typical digital camera would have, and when you place such filters over the camera lens, like especially two polarizers, those will decrease the amount of light entering the camera substantially. So you will have some noise introduced, just typical sensor noise, just by darkened light levels compared to what it would be without the filter, but you can adjust for that just by taking longer exposures. So the only kind of random noise is the same noise that you would get just from normal digital camera photography.
All right. Thanks a lot, Katherine. If there are any questions, we can take them offline. All right. Yeah. So the last talk of this session is about how objects are richer than they appear. Michael Zeeuw from Carnegie Mellon will be talking about wide baseline light fields using ellipsoidal mirrors. All right. Thanks, Vishwa, for the introduction. Hello, everyone. My name is Michael Zeeuw. In our work, we're seeking to extend the baseline of measurable light fields compared to standard, traditional handheld single exposure light field cameras. Now, these light field cameras are very useful and provide a very useful framework for capturing both spatial and angular information from the scene in a single image by using a microlens array placed over the imaging sensor. Now, one problem with these setups is that they're largely limited by their aperture and therefore only measure a very narrow cone of the available light field in the scene. And this results in a large set of missing angles that are not sampled at all using these setups. And there's a lot of very valuable information that's present over this very broad set of angles, including valuable shape and visibility cues that can be used for high quality shape reconstruction, in addition to very complicated reflectance phenomena that appear over a broad set of angles, including iridescence, where the spectrum of the reflected light changes over this set of angles. So how can we rethink the optical design of a light field camera to efficiently capture, rather than just the very narrow cone that these standard light field cameras capture, maybe extend that to upwards of a full hemisphere of light? So in our paper, we introduce a method that adds this additional step where we optically map this wide baseline light field shown on the left here using an ellipsoidal mirror to then map that to a measurable light field using standard light field measuring techniques. So to start off with, I'll go through an overview of the imaging setup for our design. So our optical design takes advantage of the use of an ellipsoidal mirror, which might have geometry like what's shown here on the right. Now, ellipsoidal mirrors have the unique property that all the light that originates at one focal point that's reflected off of the inner surface of this mirror gets mapped to the second focal point of the ellipsoid. Now we can see how this behaves over a broad set of angles. So here we're taking a very broad, wide set of angles at the lower focal point, and you can see how it's being mapped to a far narrower cone at the upper focal point. If we take advantage of this, we can place an object that we want to measure the light field of at the lower focal point, and a light field camera at that upper point. So now if we look at using just a section of the ellipsoid that corresponds to a measurable cone, we can see that from our object light field plane, this very broad set of angles is being mapped to a cone that we can actually measure at our light field camera. So this broad set of angles that we're getting is up to 53 degrees above the horizon over a full 360 degrees in azimuth. Now you note that even though we're measuring this very broad set of samples, we are missing out on this central cone. That is one limitation of our approach. We're not measuring the full hemisphere. But we will see later that this does introduce a few artifacts into some of our reconstructions. But we do note for particular shape reconstruction that the broad set of angles is far more useful than just this narrow set of cone, this narrow cone that's present in the center here. So now that we've seen kind of how we can measure these wide baseline light fields, I'll go through an outline of some unique processing that we can do to take advantage of these benefits. So in particular, we're looking at reconstructing both a 3D point cloud along with surface normals at every point in that cloud. So you can imagine if we have some textured sphere, we might have a point on that sphere that has some surface normal n. Now, all the light rays that are leaving that point in the hemisphere about that surface normal will correspond to the reflectance of that surface point. On the other hand, all the rays that are measured in the opposite direction are actually going to be occluded by the object itself. So those measurements will actually be samples on the opposite side of the object. We can visualize this for a single point
by plotting the radiance that we measure over every possible outgoing light direction from that point, as parametrized by the sphere shown in the top right. And if we do this, we can see that the upper half of the sphere is very consistent and is consistent with the reflectance of that surface point. It's largely diffuse, and there are 4 visible light sources visible from this point, which result in 4 specular highlights that we can observe in this upper half of the plot, while the lower half of the plot corresponds to the viewing directions that are being occluded by the rest of the object. So these correspond to the textural elements that are on the opposite side. And we note here that there's a very nice transition between this upper and lower region. This changes when we move off of the surface of our object. So when we move our point above the surface, as we see in the bottom right, we know that there are some rays that aren't hitting the surface of the object at all, so this black region in the middle, but also even the light rays that are sampled that are visible above the surface are actually still being corresponding to different points along the surface of the object, as noted also in the figure on the bottom right. The same is true if we go below the surface. So every outgoing light direction from this point is actually hitting a different point on our sphere and sampling all of those different textural elements. And so this behavior of moving above and below the surface and how that affects the transition between these regions is important for when we're doing shape reconstruction, so keep that in mind. For now, we're going to go into normal reconstruction, where we first assume that the point belongs on the surface of our object. And if that's true, then we can define a disk where of all the possible viewing directions V that are orthogonal to our surface normal. And this disk directly corresponds to the curve on our visualization plot on the right that is the transition between this very consistent low variance region that corresponds to the reflectance of the point and this very textured region below it. And so if we're able to produce these measurements on the right, we're able to fit a surface normal as that dividing plane. Now you may be wondering, we're not actually sampling over the entire sphere of outgoing light directions. Our ellipsoidal mirror mapping only samples some subset of this wide baseline light field. But you can observe here in this figure that even when we only sample part of it, we are sampling a sufficient amount of rays above this horizon plane and below it, and we'll be able to observe this transition region between and be able to fit a curve that divides them. And so how do we actually solve for the surface normal at a given point? We first color normalize our image just to remove the effects of shading from our variance computations. Then we compute a local variance metric. So for every light direction, we compute over a small neighborhood around that point a variance value, which is good at picking up the textured regions versus the smooth regions corresponding to a single surface reflectance. We apply a threshold to create a binary classification between high variance and low variance regions. And then we can train just a simple classifier to divide these two regions out. And you can see in this classifier, the weight of our layer directly corresponds to the value of our surface normal, because that's defining this separating plane. And so at this point, if the point is on the surface, we're actually able to directly estimate the surface normal. Now we can use this information, along with the intuition that we saw earlier, to also reconstruct a point cloud. So over a volumetric sweep, at every point, we first try to solve for the surface normal. Here we're showing an example where we're on the surface. We then compute variance over all of the observed directions in the region above that separating visibility plane. So that would correspond to the blue region in the plot here. So here we can see over that entire region, we're very consistent in the measurements that we have. So we consider that to be a low variance region globally and add that to the point cloud. If it fails, if it can't find that dividing line corresponding to the normal, it would reject that point as not belonging to our point cloud. So at this point, we're actually able to directly estimate both a point cloud using a volumetric sweep, as well as a surface normal for every single point in this point cloud. So let's look at some of our results. First, for a sphere, this is a good illustration of one of our key constraints here, is that we're assuming that the object is convex, which allows for the visibility constraints that we've looked at before to hold. So in this case, for a purely convex object, we can see even just from a single fixed camera position, we're able to sample the full view of the object and create full 3D models. And also on the right are our directly estimated surface normals from our algorithm, not used as any sort of derivation from an estimated shape. As our object becomes less convex, however, we note that there are some additional lowering the quality of our reconstructions, namely in some of the details and the recessed regions. So when that visibility, when we don't have a full hemisphere visibility, which is when the convexity no longer holds, our qualities start to reduce, but we're still able to produce fairly high quality reconstructions as well as surface normal estimates. And again, as we grow less and less convex, we have more and more errors introduced into our method, but we're still able to, even for a very complicated object, produce a 3D model that follows the general shape of it as well as direct surface normal estimates. In addition, we're able to do standard light field processing techniques with these, including viewpoint synthesis over a far broader range of angles than a conventional handheld light field camera is able to do. So you're able to see the view dependent reflectance effects in these, including iridescence on the right. In addition, we're able to refocus with a very narrow depth of field. This is again due to the very broad baseline of angles that we're sampling is in effect a very large aperture. So when we're refocusing along our focal sweep, we can produce very, very narrow depth of fields as we're going through. And finally, I'll show our lab prototype that we built to capture these images and some real results. So we follow the same optical design that we showed before. We have a section of an ellipsoidal mirror with a light field camera at the upper focal point and our object at the lower. We add a helper camera and projector to aid in our calibration of our mirror. On the right are just some few views looking down at the mirror itself. And so if we want to do the refocusing task, for example, this illustrates it well. For a glass resolution chart, we can observe very clearly the very narrow depth of field that even our real captures can simulate. So here, the resolution chart is printed on the top side of the glass, and the glass has some thickness. So as we sweep up from the bottom, we actually first come into focus on the shadow that's cast through the glass, and then it shifts to being in focus on the actual pattern that's printed on top of the glass. In addition, we're not constrained to doing focal sweeps just in the direction of our camera observations. We're also able to sweep in a direction orthogonal to our camera's observed direction, as shown here on the right. So on the left is sweeping in that standard direction, but on the right we're able to see that very narrow depth of field again as we sweep in from the side. And finally, as I mentioned before, we're hoping to be able to create some measurements of iridescence. So here's some of our real captured results. So this is kind of the output of our light field camera. And we can see all these different colors that we're observing over these different viewing directions. We can visualize this, use the same kind of plot that we saw before. So again, plotting the measured radiance over all of these outgoing light directions. Here we have 3 different points we're sampling on the CD and 3 different points on the iridescent rock. And we can see over these different viewing directions that we're sampling, the spectrum is varying very rapidly in some cases, which is clearly showing the iridescent effect that's there. So in conclusion, we've shown a designed optical system that's capable of measuring wide baseline light fields in just a single exposure. And we developed some unique processing algorithms that are capable of using these unique benefits of these light fields for shape reconstruction, and showed results both in shape reconstruction and in more standard light field processing techniques. Thank you.
Thank you, Michael, for the talk. Do we have questions from the audience? I have a couple of questions. Maybe I can get started. The first question is, you have a blind spot for your ellipsoidal mirror, right? What exactly happens if you have something like a flat piece of metal that exactly reflects light along the blind spot? Is that a pathogenic case, or are there ways to mitigate such situations?
By blind spot, you mean the central...
The missing cone.
The missing cone.
Yeah.
So you're saying if you had a flat metallic surface that was like reflecting light just into that direction. Yeah, if all of the actual reflected light was only in that direction, you wouldn't actually observe the object at all. You would observe it from all the angles that maybe would have whatever very, very low albedo it might have or anything like that. So it'd be very, very hard to observe that. But if it were shifted where the reflected light was in the direction of the surface of the ellipsoidal mirror, we would see that specular highlight come through.
Got it.
Yeah.
Yeah. Any questions? Okay, I have one more question. I believe you have not spoken about the illumination involved in the system. So is it just illumination from the ambience, or are you able to control the illumination? And is there any advantage if you introduce an active illumination module?
Yeah, that's a really good question. Our setup actually is completely passive in illumination. We don't just use ambient because sometimes it adds extra like highlights coming off of the reflection in the mirror, but we just have some uncontrolled light source illuminating the object. So it's completely passive in that sense. There are definitely advantages if you could control the illumination direction, which that is one possible future direction where you can use the ellipsoid itself to guide some sort of illumination control. If you added that, then you would be able to, especially with like reflectance measurements, if you had control of the illumination direction and then also the samples over all possible outgoing directions, you would really be very efficiently sampling like the BRDF, for example, if you wanted to fit some sort of model to a reflectance function.
Yeah. Thanks a lot, Michael. We will follow this up with poster spotlight.
Can I switch to this one? Yeah, I'm going to switch to that one. Okay. Plug that in and see if that sends audio. If not, I have a workaround. Okay. All right, this is our second set of spotlights, and so you can find the posters for these spotlights at after this. Just a reminder that we're also going, many of the other posters also have videos that you should check out on the website as well. Okay. Nope. Did you change it in the preferences? I did. Okay. I think so. Let me just check it. Yeah. So I think it's the HDMI. Okay. Does this one have a headphone jack on it? Yeah, right here. Perfect. Can you mute the HDMI channel so I can plug in? External headphones.
Wearable near-eye displays are emerging to be ubiquitous personal computing platforms with a multitude of applications in virtual and augmented reality and promising a future of metaverse. Future near-eye displays are going to be in eyeglasses form factor with a large field of view and a wide eye box. An eye box of a display is the area where light energy can be distributed. As long as the eye is present in the eye box, the user can see a clear image. Once the eye moves out of the eye box, the image is lost. Although the display optics can allow for a wide eye box, holographic display methods unfortunately places all of the light energy into a small focused region. This effectively reduces the eye box to less than 1 millimeter in size. To overcome this problem, we introduce a hologram optimization framework called pupil-aware holography. To validate our method, we built a prototype holographic display where the SLM is relayed onto a lens using a 4F system. The images generated by this display are captured by an imaging setup built to mimic a virtual eye. Here I show the images as captured on the prototype holographic display. Ground truth image on the left, images generated by conventional holographic methods in the middle, and pupil-aware holography on the right. While both methods generate images that are similar in quality when the center of the eye box is sampled, conventional holographic images quickly deteriorate as the pupil leaves the eye box. Pupil-aware holograms, on the other hand, maintains the image everywhere in the eye box. This is achieved by distributing the light energy throughout the eye box without losing the image fidelity. iBox energy distribution in holographic displays is an under-investigated problem, and we take the first step to solve it with pupil-aware holography.
Consider a camera recording two musicians practicing their acoustic guitars at the same time. While the camera has no trouble seeing each guitar separately, the camera microphone can only hear a mixture of both guitars. Even worse, the microphone is susceptible to unwanted sounds such as room echoes and ambient noises. But what if we can make our camera see the tiny vibrations of each guitar? Then we could record both guitars separately while being insensitive to the other guitar. And to the ambient noises. In this paper, we propose a novel dual-shutter imaging system low amplitude, high-frequency vibrations. Our method can sense multiple points simultaneously and can also support object motions such as the natural motions of a guitar player. We demonstrate our method by capturing various audio sources, like a speaker membrane, a chips bag reacting to a nearby sound source,
Mary had a little lamb whose fleece was white as snow,
and various musical instruments. And there's more, like vibrational mode analysis, more experiments, and the nitty-gritty details. So come to our poster to hear all about it. Thanks.
Hello, my name is Ho-Jung Kwon, and in this presentation, I'll introduce a pigment separation method that uses macro XRF element maps and mathematical optimization. Art restorers often use pigments that are different from the original artist when retouching damaged areas in an aged painting. Therefore, based on where certain pigments are present in a painting, art investigators can uncover the painting's restoration history. We assume a painting is a mixture of pigments, and a pigment is a mixture of chemical elements. Therefore, once we know distributions of chemical elements in a painting and element compositions of pigments that were used in the painting, we can derive areas where particular pigments are present. Our model uses 3 inputs to generate pigment maps, each of which shows the distribution of a specific pigment that is assumed to be present in a painting. To test the accuracy of our algorithm, we use selected areas in a sample painting with known pigment distributions and compositions. After adding random numerical noises to the cobalt blue row in the element proportions matrix, we tested whether the model could correctly reconstruct this row. We see the model correctly performs the reconstruction. The test area doesn't contain lemon yellow. We see in the lemon yellow map the algorithm correctly ignores the volume signals. Prussian blue, Venetian red, and yellow ochre have the same composition. Using color information, the algorithm catches that Venetian red and yellow ochre exist throughout the test region, while Prussian blue exists only in the purple shadows. In summary, our model can reconstruct the composition of an unknown pigment and mostly accurate pigment maps given the 3 inputs.
"3D lensless imaging has been demonstrated on numerous prototypes built in the past decade, and they can function as efficient and lightweight microscopes. But what are the resolution limits of 3D lensless imaging? This work characterizes the spatial and axial resolution limits of 3D lensless cameras. Resolution of a convolutional operator can be expressed by the modular transfer function, or MTF. If the measurements are obtained by convolving the signal with a kernel, then the Fourier transform of that kernel gives us the MTF of the system. However, the measurement operator for 3D lensless imaging is not convolutional. Previously, the lensless measurement is modeled as a summation of multiple 2D convolutions. In this work, we find a parameterization of the scene and the measurement as shown that results in a forward model built from a 3D convolutional operator. This kernel allows us to analytically derive the 3D resolution limits in terms of the 3D MTF. Specifically, the 3D MTF can be expressed by the radon transform of the Laplacian of the mask pattern. Here are some examples of 3 different mask patterns and their 3D MTF. A closer look shows us invisible frequencies in spatial and axial dimensions lie in a butterfly structure. Another finding is that all mask patterns share the same decay rate for lateral and axial MTFs. It decays quadratically with reciprocal of lateral frequency and linearly with reciprocal of axial frequency. Together, these results provide the first theoretical analysis of spatial and axial resolution in lensless images.
Hello everyone, I'm Peng Wang from Professor Li Hong Wang's lab at Caltech. This talk gives an introduction to our work in compressed ultrafast photography, or CUP. CUP holds a record as the world's fastest single-shot imaging system, which can reach tens of trillion frames per second. CUP combines the concepts of compressed sensing and a street camera. A transient event is first encoded by the pseudo-random binary pattern by DMD. Then encoded scene is relayed to the street camera, where images at different times are temporally shared in a vertical direction. We implement a regularization-based image reconstruction algorithm, TWIST, to recover the entire sequence of the ultrafast dynamics from only one single raw image. CUP surpasses all the other state-of-the-art single-shot ultrafast imaging techniques in terms of imaging speed and the number of frames in one acquisition. We applied CUPs in real-time imaging of many ultra-fast phenomena, such as light pulse reflection, light pulse propagation in 3D space, temporal focusing, photonic Mach-Cohen, optochaotic system, dissipative soliton, shockwave, plasma in laser-induced breakdown, and single-shot fluorescence lifetime imaging microscopy. CUP's imaging speed is fundamentally limited by the shearing speed of the street camera. An advanced version called CUSP overcomes the limitation and achieves 70 trillion frames per second by introducing temporal encoding in wavelengths in a tripped optical pulse. We applied CUSP to image a complex spatial temporally tripped pulse train and study nonlinear light matter interactions in a femtosecond timescale.
I'm Peter Brown from Arizona State University. I've become interested in the behavior of ciliates, a class of single-cellular organisms that generate motion using tens of cilia. Due to the small size and fast speed of the cilia, the way that they drive different swimming behaviors is not well understood. And resolving their motion requires imaging at hundreds of volumetric frames per second. Partially motivated by this problem, we've developed a multimodal microscope that combines quantitative phase imaging using optical diffraction tomography with super resolution fluorescence using structured illumination. And this allows us to resolve the cilia in 3D using the phase imaging and fluorescently labeled cargo with the SIM. We built this multimodal microscope based around a digital micromirror device, which enables pattern generation rates of up to 10 kilohertz. And due to the complicated Blaze diffraction physics of the DMD, we developed a forward model that enabled rational design of our 4-color instrument. We've imaged fixed samples of tetrahymena in ODT and SIM, and we're starting to resolve cilia in the phase imaging. Right now, we're working to improve the reconstruction and considering upgrading to a higher numerical aperture objective. We've imaged dynamic samples, Here we're looking at diffusing beads, and we can resolve how the diffusion constant changes with height above the cover slip due to hydrodynamic interactions. Most recently, we've tested a high-speed camera, which enables volumetric imaging at up to 1,000 frames per second, and we can still nicely resolve the beads. Next, we're excited to test out live cell imaging with the tetrahymena. And I'll leave you with movies of these beads diffusing in 3D at 6 volumetric frames per second, as well as 650. Thank you.
Thank all our spotlight speakers and all the great invited and paper talks that we've had this afternoon. So we're now going, this is ending the talk session of today. So we're gonna be going into coffee hour now, which is again where we had kind of coffee hour this morning over by the lunch tables. And then after coffee hour, we're gonna have our second poster session. Again, a second reminder that there are posters, there are also videos for many of the posters that you didn't see here, but you can access online. And as you're going around and looking at the posters, keep in mind what was your favorite poster and demo. Not just today, but over the last 2 days, because remember that voting is gonna end today at 9 p.m. So we're doing the best poster and best demo vote. 9 p.m. is the deadline, and then we'll present the winners tomorrow. Also, another reminder is to upload your photos for the photo competition. Remember, you don't just win fame, but also some fortune, so some prize tomorrow too. And the deadline for uploading your photos is tonight. The last announcement is that at 6:30 today, we're going to have our reception. It's going to be at the Caltech Athenaeum, as I said, so I'm sure a bunch of us will just be walking over together, but campus is small, so if you, well, you can see the map online, but I'm sure if you just ask anyone on campus, everyone will know where the Athenaeum is, so they can point you in the right direction, too. But it'll be really fun. Remember to have your purple drink tickets with you. And yeah, that's all for today. We're closing the building, so please take everything with you, and thank you again.